Okay, so hi everyone. I am Anuj Kumar. I am working as a Prime Minister Research Fellow at IIT Roorkee, and I am also the TA for this course, Trace and Ultra Trace Analysis of Metals using AAS. Okay, so this is the last assignment, that is assignment 8 of this course. Okay, so the first question of this assignment is okay, let me do full. Okay. So this is the first question in which you were asked the characteristic concentration. This is an analytical term. You have to define the characteristic concentration of an element in AAS is defined as that corresponding to how much percentage absorbance of the signal. Okay, this is the statement. Right away picked from your lecture classes. Okay, if you remember, please answer me or after, if after 1 or 2 minutes I'll explain it. Right. Okay, so this is the same slide that in which sir has defined the blank solutions. Everyone knows zero absorbance, a zero number compensation solution containing all other chemicals in the same solution concentration except the analyte. Right. If I talk about how a graph look like of a blank, right? If this is absorbance, okay, and you are scanning, so this should be the blank. There should be no analyte or any other peak. This is blank. And if analyte peak is there, there should be no interference. If there is some intensity at the same place at which the analyte is eluting, or you can say rising, so you can easily subtract that absorbance. That is basically due to the blank, and you get the actual value of the analyte, and accordingly you can calculate the concentrations. Right. Analytical curve is basically the linear curve, you can say, in which calibration curve, let's say if you have made a 5 or 6 solution containing 1 ppm, 2 ppm, 3 ppm, 4 ppm, and 5 ppm, and you noted the absorbance corresponding to these concentrations, you will get a linear plot if it is following the Beer-Lambert law, right? So this is the calibration curve, or you can also note the value of fitting. That should be point close to 0.99, right? So that is the analytical curve. If I talk about the characteristic concentration, that is basically the characteristic mass. So this is the concentration of the analyte element corresponding to a net absorption of 1%, okay, or an absorbance of 0.0044 when integrated absorbance peak area is used for evaluation, right? So if I talk about here, this is the absorbance and this is peak. So if I integrate it like this, okay, so what will be the unit? It will be absorbance seconds, right? Okay, so this 0.044 is a 1% of absorbance, 1% absorbance of the signal, right? Okay, the next one is the related to ramp time in the temperature programming in graphite furnace AAS. What it basically signifies, or what you can say, it basically defines. How can I define it in one term, right? So ramp means if you are doing a temperature programming, right? Let's say if it is 0 second and the temperature is 90 degree, right? And after 5 minutes you are going up to 120 degrees centigrade. So this is the ramp time, right? So you can say here, in 5 minutes the temperature is the temperature is changed by or increased by 30 degrees centigrade. So what the ramp time basically telling us, okay, uh, it is basically defining the heating rate, right? So if in 5 minutes your temperature is increasing by 30 degree, in 1 minute it will be increasing by 6 degrees Celsius, right? So that is why that is the heating rate. Okay, so the ramp time in temperature programming signifies the heating rate. Clear? If it is clear, I will go proceed for the next one. Okay. So the next one is uh, during atomic absorption spectrometric measurement in electrothermal AAS, the argon gas is preferably turned off. This is to ensure. So you have to basically define during measurement why the argon gas is off. Okay. So what this is to ensure, first is the trouble-free signal measurement, or you can say the longer stay of the atomic cloud in the optical path and ensure high sensitivity to avoid accident, to avoid interferences. Okay, so I'll wait for some time, and after that I'll explain. If you know already, please try to answer it. You always need a trouble-free signal. You don't want any interferences. You don't want any background, right? You don't want any absorbance due to blank, right? In ETAAS, there is a argon flow continuously flowing there. This is the chamber, okay, and the argon is continuously flowing. So during measurement, why you should off the flow of the argon? Okay, so let me define this programming. Okay, so this is a temperature programming. Here you can see in at 90-degree temperature, you uh, you are giving the 90 degrees Celsius temperature at 1 second, right? And you are holding it for 10 seconds, right? And the determination is off here, but argon gas flow is on. Okay, up to here, up to this step, the determination step is off. Why? Because all the matrix and volatiles are easily removed, right? At this temperature, the determination is on. Why? Because here we have to measure the metal, right? At 2300 degrees Celsius, the metal easily get evaporated and atomized, so it will be giving the signal. So at that time, the gas should be off and determination should be on. Why? Because there are two logics, right? If argon is flowing here, right, and the metals are vaporizing by thermal heating, so to there is a chance that metal particles go away with this argon stream, right? So there may be a loss of sensitivity also. So if the flow of this argon gas is off, right? So the atomic cloud will stay for a long time in the optical path, right? And it will ensure a higher sensitivity. Okay, so you can say the trouble-free signal measurement also, and the longer stay of atomic cloud in the optical path and ensure high sensitivity also. So that is basically to be to keep in mind that while determining the metal, the argon gas flow should be off, and right after that you should determine the metal, so that the sensitivity should get higher and there should be uh, no interference, right? Clear? Yes, longer stay of the atomic cloud, but there is also one option that is a yes, first option is also correct here, the trouble free signal measurement, right? So I am going to the next one, that is statement related to precision. Okay, so the precision is determined by multiplying the standard deviation by 2.83 for 30 or more measurements. Okay, so n equal to 30, right? Or t dot s is a standard deviation t. So uh, you have to define this parameter t. What is t here? Okay, so I'll wait for 1 minute. After that, I will tell you. So if I ask you about what is precision, what is precision? Any idea? Okay. So precision is basically the closeness of the readings you have taken. Let's say if you are doing five observations, three, four, five, and you are measuring concentration, like so. In first, you are getting 0.01 ppm, and in second one you will getting 0.008 ppm, and third is point 0.9 ppm, point 0.01, and point 0.02. So basically precision is the closeness between these values. Okay, so that is determined by multiplying the standard deviation, that is s and t. So t is basically the student factor. Okay, here you can see uh, okay, so here, right? So I have defined some of the more terms also. Sensitivity is the slope of the analytical curve is termed as sensitivity. Okay, so let me explain. uh, so if you are plotting the concentration here and the absorbance here, and 1 2 3 4 5, you are preparing a linearity of any metal and you are getting this line, right? So you will be getting some sort of this type of equation, right? So this will be the slope. Okay, so what it will define you, it will define the sensitivity, right? If I am taking this point to 2 points here and corresponding, I am plotting up to this. Okay, so let's say if here it is x2 y2 and x1 y1, right? So slope will be y2 minus y1 divided by x2 minus x1. You can calculate the slope also in this way also, right? So that will be the sensitivity. Okay, so same thing is written here, delta I by delta C or delta I by delta M. Okay, accuracy is the relate to the closeness of the agreement between true value of an element in a sample and the mean value, right? So it can be calculated by the difference between the true value and the measured value. Okay, it is clear from the statement. And the precision relates to the closeness of the agreement between the results obtained by applying the analytical procedure repeatedly. I have already explained about precision. Okay, even though the results are incorrect, right? So precision is basically not related to your the correctness of the result. Okay, if even if your results are incorrect, there will be having a precision also, right? Okay, so it is determined by multiplying with the standard deviation, that is sigma, with 2.83430 experiments or more measurements. You have to do t dot sigma. So t is the student factor. Student factor is basically telling you the probability distribution, and it depends upon the number of experiment, right? If you decrease the number of experiment, this curve, this probability distribution will be broader like this. So analysis will not be more accurate. Okay, so that is a different kind of thing. I will not explain here. Okay, so this is the student factor. Clear? Okay. Okay, so the next one is detection limit in atomic absorption spectrometer is given by this dc by d or dm by da. That is change in the concentration with respect to absorbance. Okay, into k into s, where k is a multiplication factor and s is the standard deviation. So k is a function of, first is electrical noise, optical noise, sensitivity, chemical environment, or all of these. Okay, so the detection limit. What is detection limit? It is basically the concentration that can be detected with a stated statistical certainty. Okay, okay. So you can see here this delta C by delta or delta by, it is reciprocal of the sensitivity, right? And sigma is the absolute standard deviation of the mean absorbance determined from the solvent blank. Okay, and the factor is 2 or 3, right? So detection limit is the peak area or peak height. Okay, uh, let me explain in this way. If this is a detection limit, and I can write it sensitivity like this, I can write it. If you are having more sensitivity, you can lower the detection limit, or you can say in very much low amount you can determine that analyte. Okay, this is the first thing. Second thing, detection limit you can only observe on the basis of peak area, or you can say peak height. Both the criteria is suitable for defining the detection limit, but both are the functions of electrical noise, optical noise, sensitivity, right? Metastable energy status of the analyte and chemical environment. Okay, so if you are getting a higher noise, okay, if this noise is very higher, sorry, and this is the signal, okay, and I want to determine the detection limit. If I lower the concentration, okay, so at at one time this signal will be merged into the noise, right? Okay, so it will be very hard to define the detection limit in this case. So this k factor, it basically a function of the electrical noise. Okay, and if I ask about the detection limit, okay, so detection limit is the function of electrical noise. Basically, these are the criteria on the basis you can define the detection limit: electrical noise, optical noise, sensitivity, okay, and the chemical environment, right? So electrical noise will be the right answer. Sorry for I have written here. So the next question is: in the body fluid analysis, what assay is necessary to release aluminium, calcium, alkali metals, or alkali and alkali earth metals? So try to answer it. I'll waiting for 2 minutes because this question is related to the application part. Okay, if you are unaware about the applications of AAS, how you can think about your sample that it will be analyzed by AAS or not, right? So wet assaying, what is wet assaying? Is basically the procedure to digest the sample in the acidic medium, right? So the same thing is mentioned here. The treatment of the sample with nitric acid is called hashing. Okay. So if I talk about the one of the specific applications of AAS, first is the body fluid and tissues. Okay. So the determination of calcium, magnesium, sodium, and potassium, iron, copper, and many other metals in body fluids such as urine, serum, and other biological materials are the most important applications of these techniques. Okay. So the tissue samples, for obvious reason, must be wet or dry as before analysis, because analyzed aluminium is an element of focus in brain tissues. That is basically the reason behind the Alzheimer's disease. Okay, in many other analyses, arsenic, mercury, cadmium, selenium, other metals are of very importance. But in the tissue, in the brain tissues, or you can say in tissues, aluminium, uh, you should do the assaying before analyzing the aluminium in body fluid analysis. Okay, so aluminium will be the right answer. Okay, other other metals are also the determination of calcium, magnesium, sodium, basically the alkali and earth metals. Okay, they can also be determined by the atomic absorption spectrometry. Okay, but in tissue, aluminum is very important, so you should do the uh, assaying procedure, wet assay, right? The next is related to the analysis of foods and drink. Okay, so why digestion with nitric acid is preferred? Okay, it bring tissues in solution, plant and food residues. Sorry, residues in solution, pesticides into solutions, or all of these. So in a case of Analysis of foods and drink. Nitric acid, basically what it does, it brings tissues in solution. Okay, you can see here. Uh, Basically, in food, there are many contaminants like fertilizers, okay, insecticide, pesticides, okay, and some proximity in the close proximity to the roads, industrial installations, metallic elements are present in food stuff, okay. So they burn to functional group tissues. Most of such tissues are digested with nitric acid to bring them into the solution, okay. And also help similarly, almost all dairy products must be wet before analysis, okay. So lead is very common contaminant in foodstuffs. This is tin is also added to plastic foils as a stabilizer, right? So these are some applications. You can read more details. There are many more details, many more applications in the on the web. You can check, right? So these are the specific applications. They are in routine analysis. Routine analysis, if I talk about, right? So the function of nitric acid is basically to bring the tissues in the solution. Okay. The next is related to the analysis of rocks and minerals. Okay. Why rocks and minerals are always digested with HF? This is also a acid or H2SO4 because a strong acid it is. Sorry. So why it is so? It helps in silica and metal oxides in dissolution. It helps in the dissolution of silica only. It helps in the dissolution of sulfides or oxides, or all of these. It is a weak base actually, weak acid. Sorry. So calcium, magnesium, potassium, and all these metals in rock samples is regularly determined by AAS. Okay. So digestion with HF and sulfuric acid is the most preferred technique for materials. Sorry, minerals. Why? Because it it helps in the dissolution process of silica and metal oxides. Okay. What is basically silica is basically easily dissolved in presence of acid, okay. So if I dissolve the rock and mineral sample direct in acid, so silica will be easily dissolved, right? And HF can convert into the silica fluorides which are easily decomposable, and it also help the metal oxides also. And if there are metal oxide, it can easily uh, analyzed by the atomic absorption spectrometry. So first option will be the right answer. Okay. So if you want to study in very deep about the applications, you can read more research papers about the applications. There are many more treatments like matrix modifier is added, and treatment with different acids, content of acids are changed, and what is the impact on the sensitivity, right? What type of interferences you usually deal with, right? The next is related to the analysis of plastics and polymers. So why plastics and polymers are digested with this sulfuric acid or hydrogen peroxide? Why? There are five options. Polymers get degraded easily. Packing material dissolved in sulfuric acid. Organosilicons can be dissolved. Organotin can be dissolved. Or all of these. Plastics and polymers are the long chain compounds, and they are basically organic. If you are adding this oxidizing agent or acid, what will happen? The organic content will be easily degraded, right? Or it can be converted into their oxidized products like carbon dioxide, right? So what it basically does, it degrades the polymers, it breaks down the organic part, okay, and it free the metal for analysis in AAS, right? So this will be the right answer, and this is basically a compact discussion related to the plastic, textile, and paper. Okay, some scientists determine these metals in paper pulp and cellulose directly. Okay, these metals are routinely determined in plastics, okay, such as polypropylene, nylon 66, polystyrene, PVC. Okay, soluble polymers are dissolved in, this is the solvent, methyl isobutyl ketone, cyclohexane, formic acid, and they are aspirated directly. But in case of insoluble polymers, we have to do a pre-step, that is the digestion with sulfuric acid or hydrogen peroxide mixtures. Okay, uh, this is the basically abundance. Organotin compounds are added as stabilizers in packing materials. In that case, the plastic sample is extracted with 3% acetic acid or these different solvents, and the extracts are used directly in graphite furnace AAS. Okay, organosilicon in paper can be extracted with petrol, evaporating the solvent and taking up the residue in this solvent and aspirating directly. Okay, so these are different applications. On the basis of metrics, you can define what type of treatment you have to give to the sample. Okay, but in case of insoluble polymers, first you have to digest the sample with sulfuric acid or hydrogen peroxide mixture. So that's because the organic compounds interfere in the analysis. You know about the interferences caused by the organic compounds. So basically, first you have to digest and then you have to analyze the matter. Okay, and this is the numerical type question. Okay, you have to calculate the percentage RSD, that is relative standard deviation, as well in concentration, this one, and as well as in the absorbance value also. Okay, so this is an experiment. One is measuring the calcium in water solution. The following findings were observed. Okay, uh, in this problem, the analyst already set a linear curve. Okay, and he or she is measuring only the unknown values. Okay, so if I am getting the absorbance value of 0.56, that is basically telling me that is the water is containing this much, 1 ppm of calcium, right? So these readings are taken. This is basically the repeated experiment, 5 replicates experiment for the same unknown solution. Okay, so you have to calculate the percentage RSD value in this concentration and absorbance also. Okay, so let me insert first the blank slide here. So what you have to do uh, for concentration, right? First I am calculating the percentage RSD in concentration. Okay, if I categorize these values x1, x2, x3, x4, and x5, right? So you can calculate the average value, that will be x1 plus x2 plus x3 plus x4 plus x5. Since the number of experiment are 5, that will be 5. Okay, from here you will be getting the value of average. After that you can apply the formula for standard deviation. That is basically x bar minus x1 ka square plus x bar minus x2 whole square plus up to x5 and divide by n minus 1. N is basically 5 here. So 5 minus n 4 and 2 will be out of this under root. Okay. So first you have to calculate the average value, then you have to subtract first value and then square it, then second value, third, similarly for up to fifth. Okay, and you will getting the value of standard deviation. But in question, you are asked about the percentage RSD value. So in for percentage RSD, what you will do, that is standard deviation divided by average multiply by 100. So that will be your percentage RSD value. Okay, you can solve easily, right? Or let me just uh, do in Excel. If I am writing here 1.99, 1.04, 0.98 and 1.05. Okay, so if I am calculating the average, this will be the average of these values, right? And if I calculate the standard deviation, okay, and RSD will be this one divided by this one. This will be the RSD value, that is 3.077%, right? By putting the formula, you can cross verify. Okay, okay, you can just put the values and in on in that formula. Similarly, if you want to calculate for absorbance, okay, 60, that will be 4.56, something like that. Okay, you can cross verify by putting the values in the formula, right? So this was all about this last assignment. If you have any question, you can put the question in discussion forum. I will answer there. Okay, and best of luck for your exam. Okay, is it clear? Okay, thank you very much for attending. If you are if you will be having any problem or will be facing any issues, you can post before exam in the discussion forum. I will be available there for answering all the queries. Okay, so again, best of luck for exam. Thanks a lot for attending the session. I'm leaving the meeting now. Thanks.